So now for the final talk in the project 16, I would like to call Sara Morais.
So, good afternoon for everyone. My name is Sara. I am postdoctoral researcher at Department of Fundamental Chemistry of University of São Paulo under supervision of Professor Ataopa Braga. So today I will talk about where we are performing in terms of DFT study of hydrogen adsorption and methane adsorption at Cu-SSZ-13 zeolites. So, as we know, there are necessity to find alternative fuels and feedstocks, chemical feedstocks, and methane is a great alternative because is abundant, inexpensive, and has a great versatility to applications as a feedstocks. In the graphical, we can see that the projected production of natural gas will be increased, and the consumption is increased as well, but not in the same value. There will have more production of natural gas than consumption, and because of that, we have to find ways to valorization of methane. And why is so difficult to valorize? Because the methane has high bond energy and high symmetry, low polarizability, and all these features makes it necessary use high temperature and high pressures to oxidize methane to high value compounds. Because of that, the main of methane production of today is flared. So the dream reaction will be oxidize methane with low temperature and low pressures. To do that is several strategies for valorization of methane, and one of that is to mimetize the behavior of uh, methane monooxygenase enzymes. So we exchanged zeolites with copper sites with oxygen, oxygen active the sites, and Grutard getting a selective oxidation of methane in zeolites copper containing. So theoretical calculations is very important to study these systems in terms of reactivity, and to on final goal is a rational design of zeolite clusters and explain some features of these systems. So this work is the work what we basing on this work to build a cluster to study these adsorptions. So we cut off with Python automated with a Python automated system, and we cut off from the crystallographical information file of the Chapazita zeolite with sizes of 3, 4, 5, and 6 angstroms. we perform a benchmark with 6 functionals and base sets DFT SVP. So we have the A with size 3, B size 4, C size 5, and D size 6. So to validation of our clusters, we search for a simple reaction that we have experimental results. So there's the more simple reactions we search was the hydrogen adsorption at the Cu-SSZ-13 light. And the hydrogen can be adsorbed at Cooper on the 6 membered rings here in the 6 membered rings and 8 membered rings. So to analyze our systems, we did statistical analysis, thermochemical analysis, ASP, NBO, and NCI analysis. So we have our clusters here, and in here we have the hydrogen adsorbed at the 6 membered rings, and here at the 8 membered rings. So we in the statistical analysis, we verified that B3 LIP was the best functional with lower deviations, and we observed that when the hydrogen is adsorbed at 6 membered rings, the hydrogen, the Cooper, is out of plane to interact better with the hydrogen. When it's bare, the Cooper stay in the plane of the membered rings. And it's a result that was observed experimentally, that the hydrogen, the Cooper stays out of plane to interact better, and is increase of the adsorption when Cooper is out of plane. In terms of energy, we observe that clusters C with 5 angstroms present the best results in terms of heat of adsorption. The experimental value is 3.8, and we get the best results for the cluster 5 size. And B3 LRP was the best functional because had less fluctuations in the heat of adsorptions. However, the best punctual results was with PBE and omega B97XD. So for the adsorption at 8 membered rings, we observed again that cluster 5 size was provide the best results, and B3 LIP was the best functional as well. To understand why the 5 size was the better against the 6, we did the analysis of electrostatic potential maps, and we observed that the C clusters has a polarization increase of the polarization at the zeolites, and we believe that this feature is related to a better interaction entre hydrogen and in Cooper, and make this size better to the description of the reactivity of the site. So we performed NBO analysis, and we observed that the interaction of the hydrogen with the copper uh, occur through a back donation, a donation of the orbital sigma of hydrogen and back donation of copper to the antibonding of hydrogen. And we observed that because the six-membered rings has a higher donation from the zeolites, from the oxygen of the zeolites, the back donation is lower for the six-membered rings against the eight-membered rings. So we did NCI analysis as well, and we observed that these green points here show that the zeolites interact more with the hydrogen molecule in the eight membered rings against the six-membered rings. So now to we study the methane adsorption at the zeolites and study the DC8 activation, we made it we activate the site. We put another copper atom and activate it with oxygen, and we change the aluminum position, and one of the aluminum position is here, and the second can be here with two T sites of separation, or here with three atoms of separation, T sites of separation. And we find that when we put three types T site separation, we have about 0.4 of kilocalories. So when we calculated the coordinate of reaction, we observed that when we have the systems with two T sites of separation, we have activation energy about 10. And for the three T site separation, we have about 8. And the experimental value for that is 23. And we have underestimation of the energy barrier. But when we compare to literature, we observe that we have a value some closer, and these calculations was made with periodic simulations at VASP. So our conclusions that when we started this work, we want to get switchable clusters, and we believe our delta cluster method was switchable for these calculations. The structures was maintained. The clusters 5 presented the best fit in accord to previous works. B3 LP functional was the best for H adsorption. And in relation to methane, we observed that our results was comparable to periodic method, but in relation to experimental, the energies was underestimated, and we want to use another functionals to getting closer to experimental values. So I would like to thank you for your presence and my colleagues of the laboratory and the shelf of SPN. So thank you.
Okay, so now open for questions. Anyone?
Thanks for the nice talk, Sara. Sara, when you mentioned there for the adsorption of hydrogen, you mentioned that the bit-leap functional provides the best result. But this statement was based only on the adsorption energy of H2 on copper. That's right?
Yes.
For example, if you look at a wide range of properties, like the adsorption, bond length, if you could compare different experimental results, for example, could you try to say to add additional properties to see if this statement stays true? Because if you base this statement only the absorption energy is only one variable, it can be just accidental. That's the comparison is good.
Yes. Another property, experimental property, was we analyzed the statistical deviations of the structures. The values of the structures, we use the experimental values. And for B3LP was the lower deviations from the experimental results for structure. But for methane, for example, the result was underestimated, and because of that, we will try to another functionals and another reactions as well. We want to change the metal as well.
So we have time for another question. Anyone?
Okay, along of your talk, you mentioned also that the PB functional, you highlight the PB functional as one that could provide a reasonable, to say, data quality for the, I think, for the structure and for the absorption too. What is the difference in computational time between the PB functional and the bit-leap for the particular case of this material, this system? For example, if you pick up the hydrogen to the absorption there, if you compare the bit-leap and the PB.
In time of the machine is not greater time. I think it was less than 1 day in time of calculations in real time in days. Between all of them, we have no great difference of time in terms of days. We have these results. I forgot to put in my, but the difference is not so great. The only difference that was great was the first optimizations, because it's not optimized yet, but the rest of the functionals is not a great difference between them.
Several of your functionals belong to the category classified as a hybrid functionals, but some of them are like PBE, are general DGA functional that has a lower computational cost compared with the hybrid functional. Means I was asking, but you are mentioned that the computational cost is similar for all those functionals.
Was similar. I don't remember the value, but in terms of days was similar.
Okay. Do you have more questions? No. So. Oh.
Could you give more details about the way you take from the crystal structure to the
Yes, yes. So I believe that here is better. So we get the C file, and Basin developed a Python automated form to cut. We choose the active site, the point of we trace radio R, and can be 3, 4, 5, and we cut off this and generate a cluster. So our work was different from the literature because we not choose no one that has the cluster open. We choose only the clusters that have the ring closed. So after that, we choose silicon to change for aluminum, and put copper, loaded the copper at 6 membered rings or 8 membered rings.
Okay, so let's thank Sara.
Thank you.
Okay.